Differential equations give us a flexible language in which we can describe the relationship between quantities and their rates of change. But so far, the only way we have to solve them is essentially to guess. That'll only get us so far. But there is a way to solve certain differential equations by taking a familiar technique and turning it on its head. Last time we talked about the importance of making connections in mathematics. I want to take a moment to develop that thought just a little bit more, since that's what's going to help us start being able to actually solve differential equations for real. In high school algebra and pre-calculus, you learned about all sorts of different kinds of equations. Linear equations, quadratic equations, polynomial equations, exponential and logarithmic equations, trigonometric equations, and so on. It's easy to get the impression that these are all separate, with each one needing to be solved in its own way. But if you think about it, everything you ever did when you solved equations hinges on just two techniques: undoing and splitting. Just about any algebraic equation you learned about can be solved using one of these two techniques. Think about this example. 3 times the absolute value of the quantity 2x plus 1, all minus 4, equals 5. Try pausing the video to see if you remember how to actually solve this on your own, and then we'll go through it together. No judgment if you don't remember. Okay, so first we'll try to get that absolute value on its own. It's been multiplied by 3 and then subtracted by 4, so we need to undo each of those things. First we add 4 to both sides, and then divide both sides by 3. So now we have the absolute value of 2x plus 1 equals 3. At this point, we could think, what do we know about absolute values? Well, the absolute value of a number is its distance from 0, which is always positive. So if the absolute value of a number is 3, the original number could have been positive 3, or it could have been negative 3. That splits our equation up into two different cases. Either 2x plus 1 equals positive 3, or 2x plus 1 equals negative 3. Each of these equations has its own solution, which you can find with more undoing. In the first case, x equals 1, and in the second case, x equals negative 2. The things we did here are at the heart of just about every algebra problem. The way you undo or split things might differ depending on your situation, and you might have various bits of cleanup along the way to get like terms together and such, but the overall problem-solving strategies are still the same. And believe it or not, they work for not only algebraic equations, but differential equations as well. It's about that time of year when it seems like everyone's thinking about turkeys. Whether you're getting ready for a big holiday dinner, or just looking to do some meal prep for the week, there's something distinctly comforting about the smell of a freshly roasted turkey. Or if meat's not your thing, just replace it with tofu, I guess. But you have to be careful to cook it properly to make sure it's safe to eat. Most sources say that turkey is safe to eat when the breast reaches an internal temperature of 165 degrees Fahrenheit. There are some who claim it's 180 degrees Fahrenheit. I think those are the same people who like their steak well done. Anyway, picture this scenario. You've heated your oven to 325 degrees Fahrenheit. You open your fridge, take out the turkey, which has an internal temperature of 37 degrees Fahrenheit, and at noon, you put it in the oven. An hour and a half later, you check on the turkey and find that its temperature has risen to 103 degrees Fahrenheit. How much longer do you have to wait until that delicious turkey is fully cooked to 165 degrees Fahrenheit? To figure this out, you have to know a little bit about how temperature change works. When we first put the turkey into the oven, there's a huge difference between its temperature straight out of the fridge and the ambient temperature of the oven. That big difference will make the turkey start heating up pretty quickly. But as the turkey's temperature gets closer to the ambient temperature of the oven, that heating process will start to slow down, and each extra degree will take just a little bit longer. What we've just described here is known as Newton's law of heat transfer. It states that when an object at one temperature is placed into an environment with a different ambient temperature, the rate of temperature change of the object will be proportional to the difference between the two temperatures. By the way, most sources actually call this Newton's law of cooling, which can be kind of misleading because it also works for heating. To answer our question of when the turkey will be ready, we need to solve this differential equation. This one looks sort of similar to the exponential growth we saw last lesson, but now there's an extra term in there for ambient temperature. That makes it a bit harder to just guess at a solution. And let's be honest, we don't want to be stuck with guessing being the only way we know how to solve these. So it'd be nice if we had a way to actually solve the differential equation, kind of like how we solve algebraic equations. Well, there is a way. And interestingly enough, it's kind of like a backwards version of something you've seen before: implicit differentiation. Think back just a few lessons to when we did implicit differentiation. Given an equation in two variables, say x and y, we took the differentials of both sides and then rearranged the terms to solve for dy over dx algebraically. Well, if we could somehow reverse this process, it seems we could recover the original relationship between x and y. That technique is called separation of variables, for reasons that'll soon become clear. Okay, so let's see how separation of variables applies to our problem. To begin with, we'll get everything involving temperature, big T, to one side, and everything involving time, little t, to the other side. So that gives us d temperature over temperature minus 325 equals k times d time. If we write that first fraction as 1 over big T minus 325 times d big T, then we end up seeing that each side of the equation is a differential involving just one single variable. We've separated our variables, hence the name. Now, how do we undo a differential, which is just a derivative times an extra d something? Well, we look for an antiderivative. An antiderivative of the left side would be natural log of absolute value, big T minus 325, and an antiderivative of the right side would be k times little t. But remember, each of these could have an extra constant added on, so we'll add plus c to the right side. Wait, why just the right side? Well, really either or both of these antiderivatives could have had their own constant on it, but then we could just use a little algebra to bring both the constant terms over to one side, so we really only need to put the constant on the side that's most convenient to us. At this point, what we have is an implicit equation that relates the temperature to the time. We can nail this equation down just a little more using our given information. If we let t equals 0 stand for noon when we put the turkey in, then we have the natural log of absolute value 37 minus 325 equals k times 0 plus c. So c is the natural log of 288. That's about 5.66296, but I'm actually going to leave this as natural log of 288 instead of writing down the decimal. You'll see why soon enough. Also, by the way, this is why we need that absolute value after the natural log whenever we're doing integration. We can't take the natural log of negative 288, at least not without imaginary numbers getting involved. Okay, we've got c, now let's find k. We also know that at t equals 1.5, that is 1:30 p.m., we have a temperature of 103. So that gives us the natural log of absolute value, 103 minus 325, equals k times 1.5, plus natural log of 288. Solve for k, and we get about negative 0.173522. I'm going to keep calling that number k out loud, just to make things saying things out loud a little bit easier. So now our implicit equation describes a situation with the turkey. We're getting somewhere, but we've still got a little more work to do. So we've got an implicit solution. That's not bad. But what would be really nice is an explicit solution, a formula for temperature as a function of time. So let's do some algebraic massage to make that happen. First, we can get rid of the natural log by raising e to both sides, since exponential and logarithmic functions are inverses of each other. So now we've got the absolute value of temperature minus 325 equals e to the power of k times time plus natural log of 288. Remember, k is the value we found earlier. Then we could use our exponent properties to split that up into e to the natural log 288 times e to the kt. And again, since exponential and logarithmic functions are inverses, that first part just cancels out to 288. That's why we kept the natural log intact. It cancels out so nicely. Now, how do we get rid of that absolute value? Well, remember we just talked about absolute values a few minutes ago? We could split that absolute value equation up. Temperature minus 325 could be 288 times e to the k times time, or it could be negative 288 times e to the k times time. So there are two possibilities. Or are there? Actually, only one of these possibilities makes sense. But which one? This is why I often stress to not just push symbols around on a page, but think about what they mean. Remember, big T is the temperature of our turkey. Its temperature is less than the 325 degrees of the oven we put it into. So the temperature of the turkey minus the temperature of the oven should be a negative number. So that means we want the right side to be negative 288 e to the kt. Since e to the kt is guaranteed to be positive, that whole right side is guaranteed to be negative. We used the information we knew about the problem to make a decision about which solution made more sense in context. So there we go. All we have to do now is add 325 to both sides, and boom, the temperature of our turkey at any given time t is 325 minus 288 times e to the quantity negative 0.173522 T. And if we use a little more algebra to figure out when the temperature comes out to 165 degrees Fahrenheit, we get T is about equal to 3.387 hours. So you've got a little under 2 hours left until you get to take that delicious turkey out of the oven. By the way, if we'd done this in general, instead of sticking to our turkey situation, we'd actually end up with the following solution in general to Newton's law of heat transfer. The temperature of an object in an environment at any given time is equal to the ambient temperature plus the temperature difference, object initial temperature minus ambient temperature, times e to the kt, where k is the constant of proportionality between temperature change rate and temperature difference. This works whether the object is heating up or cooling down. Now, I bet at least one of you is thinking, who on earth would go to all that work just to figure out when your turkey's going to be done? And my answer is, you'd be surprised. A German-American physicist at Stanford named P.F. Panofsky was once unsatisfied with the 30 minutes per pound rule for cooking times for turkeys. So looking at the ratio between surface area and mass, he came up with his own formula for how long it should take to cook a turkey. And as recently as 2021, in a journal from the American Institute of Physics, an article did a full in-depth analysis of justifying that formula, using, you guessed it, differential equations. Mathematical modeling is a powerful tool that just about anybody can make use of. If you can use numbers to describe something, you can use math to analyze it. It goes to show how calculus reaches not just into every branch of academic study imaginable, but also into our daily lives, whether we actively realize it or not.